I'm gonna go ahead and start recording, you guys. Okay, so let me go ahead and do this. Okay, weekly activities folder. So y'all, we are in week 8 right here. Week 8. Let me click on this. Okay, all right. So again, y'all, we didn't have class Monday, right? That was me giving y'all the day to take the test. So today, my original plan, y'all, was for us to go over sections 4.2 and 4.3. And 4.2 is not a super long section. 4.3 is a little bit longer. So what I decided we're going to do today, y'all, we're going to hold off on 4.2. We're going to go directly to 4.3. You don't need to know 4.2 in order to do 4.3. So I want to go ahead and hold off on that one. When we come back from spring break, I've already made the notes for the week that we come back. We'll probably double up on 4.2 and 4.4 that Monday that we come back, and then we'll continue with the rest of chapter 4. But I want us to go to 4.3 today. So y'all, I do have the notes right here again. So if you click on the link, it should give you the notes in PDF file. And what I did is I went ahead and printed them out already. So let me scroll the way down here towards the bottom. And that's 4.1, which we did the other day. So, yo, I'm going to move the 4.2 homework out of this week folder, and I'll put it in the one for week 9 when we come back from spring break. Um, so we're going to go over 4.3 today, okay? And guys, just a reminder, the homework for 4.1 is due the Wednesday that we come back from spring break. And this one too will be due that Wednesday. Now I'm going to move 4.2, so it'll be due later on. You want to click on it, you're more than welcome to, but you don't need to worry about it right now. I'm just going to move it to a different folder. But we'll worry about 4.2 when we come back from spring break. All right. So, 4.3 is something that we call maxima and minima. So these are basically highs and lows, right? Maximums and minimums. Okay. So we're going to talk a little bit about absolute extrema, local extrema, how to find critical points of a function over a closed interval, and then how to use critical points to locate either absolute extrema over a closed interval. Okay, so we got a little definition here. It says let f be a function defined over an interval I, and let c be an element of I. So c is it's just going to be a number in that interval. Okay, so I don't know how much exposure some of you have had to like notation like this, but I'm just going to kind of give you some. C is an element of I. That little E, that's the Greek letter epsilon. The way I read that is an element of. Okay. And again, like I know Jennifer said she's thinking about majoring in math, so Jennifer's probably going to see a whole lot of these symbols as you go along. And those of you who end up taking like Cal 2, Cal 3, you're probably going to see some of them too. But I just kind of want to, give you some information on that. All it says is we have an interval, okay, and we're taking a number out of that interval. So we say that f has an absolute maximum on that interval I at c if f of c is bigger than or equal to all the other numbers in there, okay? And we say that f has an absolute minimum on the interval I at c if f of c is smaller than every other point, smaller than or equal to every other point on that interval. And then we have a absolute maximum at on I at C, or an absolute minimum. We say F has an absolute extreme. Okay, so look, let me kind of explain what we're talking about here. So this graph here, y'all, the first graph here, this is the graph of f of x equals x to the third. So remember, y'all, even though a lot of times they don't do it, there's little arrows here, right? What does that mean? The graph goes up and up forever, and it goes down and down forever. So there is no absolute maximum, and there's no absolute minimum. Why? Because the graph continues to go higher as I'm going to the right, and it continues to go lower as I'm coming in from the left, right? Now, here's the graph of f of x is equal to 1 over x squared plus 1. And it says, look, we have an absolute maximum of 1 at x equals 0. What does that mean? The highest point in the graph, y'all, is that point right there. That's what we call it, the absolute maximum. The graph never goes above 1, and it hits 1 when x is equal to 0. That's right. Very good. So guys, John says, look, the way the graph is moving, this here would be something that we call a horizontal asymptote. And so the graph is getting really, really close to that x-axis. It never touches it. So that's why John said it approaches 0, right? It never, so the limit as I go to the right is the limit as I approach infinity. We're going to talk about that later in chapter 4. Or the limit as I approach negative infinity, as I come to the left, my y values are getting closer and closer to 0. That's right, John. So that's why it says that there is no absolute minimum. Okay. And then now we have the graph of y equals cosine of x, right? Or f of x equals cosine of x. So there's an absolute maximum at x of 1 at x equals 0. And x is equal to 2 pi. And x equals 4 pi. And also negative 2 pi, negative 4 pi, so on and so forth. So for even multiples of pi, we're going to have that maximum at 1. And then we're going to have a minimum of negative 1 at odd multiples of pi. So pi, 3 pi, 5 pi, 7 pi, also negative pi, negative 3 pi, negative 5 pi, negative 7 pi. So we have both an absolute maximum, and those maximums occur at the high point. And we have absolute minimums, and those minimums are, again, what we call the low point. Okay? All right, so again, this is what we're talking about, absolute maximum, absolute minimum. Sometimes graphs have an absolute max, and sometimes they don't. And sometimes they have an absolute minimum, and sometimes they don't. Sometimes they don't have any absolute, right? And sometimes they have both. Okay, so the next portion here, y'all, says, if f is a continuous function over the closed bounded interval from a to b, then there is a point in that closed interval AB, which has at which f has an absolute maximum over that closed interval, and there is one point in that closed interval where f has an absolute minimum over the closed interval. Okay, what this means, y'all, is if we were to look at a graph, okay, and we're going to restrict it to some closed interval a and b, okay, and I'm just going to draw some kind of a function, okay. I don't know what it's going to look like, but I'm going to do something like this. Okay. So what it's saying, and actually, I'm going to fix it a little bit because I don't want it to look a certain way. Okay, so this point right here, y'all, is f of a, and this point right here is f of b. What the extreme value theorem says, when we restrict the domain to these values, the graph is going to have a high point and it's going to have a low point. So we might say, look, there's some value here where this is the highest point, right? And I try to kind of draw a little bit, and maybe I didn't get it as good as I wanted to, but like you might say, look, right, just a little bit to the left, that might be lower. There's a point where that point is lower. That's all it's saying. That's what the extreme value theorem says. If you restrict the domain, you're just looking at that one picture, there's going to be a point that's highest above all of them, there's going to be a point that's lower, okay? So, definition, it says a function f has a local maximum at c if there exists an open interval I containing c such that it's contained in the domain of f, and f of c is bigger than f of x for all x in that interval. And a function f has a local minimum at c if there exists an open interval I containing c such that I is contained in the domain of f, and f of c is smaller than all of the f of x. Okay. You may have. There might have been stuff that you talked about. It's possible. I mean, even in college algebra, we talk about like highs and lows when we talk about graphs. Yeah. So we're just kind of revisiting it, but we're going to do the calculus part of it in this class. So take a look here, y'all. I got a picture of a function, right? Again, I don't have a definition for this function, but this is my function f. And look what it says. It says that f of x is defined over the interval of all real numbers. Okay, so the debate is all real numbers. It says we have a local maximum at x equals 0 and a local minimum, a local maximum at x is 0 and x is 2. So what does that mean? It's telling me that I have two high points. This is a high point, and that is a high point. They're high points. They're not, I know one of them is higher, but they're still high points. That's what we call them local maximums. Okay. So basically, anytime you have a little hill or you have a peak, we're going to have a local maximum. Guys, those local maximums may also be absolute maximums. So all it means for it to be absolute is it is the highest one. Okay. So local means you have high points or low points. Absolute means it is the highest or the lowest. Yes, Doug? At 2, that's right. That's right. Very good. So John is saying the absolute max occurs when x is equal to 2. That's right. And then we also have a local minimum, right? We have a local minimum at x equals 1. Y'all, just looking at the way the graph is drawn, you agree with me that that graph goes down that way and it goes down that way? Okay, question. Do we have an absolute minimum? No, because the graph goes down and down and down forever, right? In order for us to have an absolute minimum, y'all, there would have to be a point that is lower than all the other ones. And because the graph goes down forever and ever and ever, there could never be an absolute limit, right? Because you could say, look, oh, I found the lowest point. And we would say, well, did you really find the lowest point? Because it continues to go forever, right? Oh, at? You know what I mean? Like that? Yeah. Like, you know, like on social media, on Instagram, if you tag somebody, right? At. Oh, there you go. Emails. I don't know why I didn't think about that. Very good. Good point. And then, John, look what you said. The local maximum at x equals 2 is also the what? The absolute max, right? Okay, good. That's awesome. Okay, so definition, it says, let C be an interior point of the domain of F. We say C is a critical point if the derivative at C is 0 or the derivative at C is undefined. Okay, so now we're going to talk about critical points. Critical points occur when the derivative of the function at that point is either 0 or the derivative of the function at that point is undefined. So let me show you what we got here. We got a couple of pictures. Okay, so we're going to talk about Fermat's theorem in a little bit, but it says, I want you to look at this one here. We found the derivative, and remember when we're finding the derivative, y'all, we're taking the equation of the tangent line, or the slope of the tangent line, right? So the slope of a horizontal line, isn't it 0? Okay. Now, anytime we have what we call like sharp points, so like if you look at B and look at C, those are sharp points, right? The graph kind of comes up, it's like a point. Like if you had a balloon and you drop the balloon right here, you know it's going to pop, right? So anytime we have sharp points, y'all, the derivative is undefined, okay? Because we can't take the derivative at those sharp points. It's not going to, we can't do it. It has to be a smooth, continuous function. It can't have those kind of sharp points in there, okay? Guys, the other thing here, if my derivative at a point is a vertical line, it is also going to be undefined, okay? So notice these here are vertical, undefined, and if I have this kind of a sharp point, it's also undefined, okay? Now, even though the derivative here was undefined, we still had a maximum because that was still the high point in my graph, right? And even though the derivative here was undefined, we still had a minimum, okay? So Fermat's theorem here, y'all, says if F has a local extremum at C, so if it has either a maximum or a minimum, and F is differentiable at C, then the derivative is going to be equal to 0, okay? So let's take a look and see if we can do this first problem here. So y'all, I took this problem directly from your homework, okay? Right? Yeah, we've talked about graphs like this before, okay? So look at the directions. It says use the function f graphed above and answer the following questions. It says note we're going to have to estimate some answers. So guys, when you're estimating, remember what an estimate is. It's a guess, it's a good guess, right? So you shouldn't be out, if it's not working out, it's probably because we're guessing way too off, okay? So, well, hold on. Let's go through the problems and then I'll come back and answer your question. But I want you to look at the first part here. It says the local maximum F occurs at. Here, y'all, when it says occurs at, they are looking for the X value. Okay? Yeah. They're looking for the X value. So we're talking about the maximum. Everybody agree the maximum is the high point? Okay, so that's going to be my high point. What would you say my X value is right about there? 1/2 or 0.5. Okay, so let's go with 0.5, right? Either way, 1/2, 0.5, same thing. Now, when we get to the second part, y'all, when it says what the local maximum of F, this part is asking me to find the Y value. So would you say the Y value 0.5 maybe, 0.4, something like that? 0.5? Okay, let's go with 0.5. Okay. Local minimum. When does the local minimum of F occurs at what? Remember, we're looking for the X value. What's the X value here? Very good, -3. Okay. What is that local minimum? -6.5. Okay, -6.7, right? So remember what we're doing. It says we need to estimate some answers. So our guesses, there's going to be a tolerance when you put these kinds of things in, right? So if you put like -6.5 or 6.6 or 6.7, you're probably going to be okay. If you were to put -6, that's not a good guess, right? Because we know it's further, we know it's lower than -6, right? So again, it's an estimate. Estimate's a guess, but it's a good guess, right? So if you put like, oh, -20, yeah, you're way off there, right? Even if you put -7, you're off. We know it's between -6 and -7, so pick a number between there, right? That's what they mean by estimating. Okay. All right, let's take a look. So it says the function f of x has two critical numbers, and we want to find them. Okay, y'all. So look, I'm going to kind of scroll back over here because I want to talk about something real quick. And let me see if I can find it. Here we go. Okay, critical points. Critical points occur when the derivative is equal to 0, or it's undefined, right? So what we're going to do is we're going to come back over here, and we're going to look at this function. Okay, so number one, this is a polynomial, right? So polynomials, y'all, are continuous functions and they're differentiable, okay? Meaning that we can take the derivative. So the first thing we want to do here, we want to find f prime of x, okay? So let's find the derivative. What is the derivative of 2x to the third? 6x squared, very good. Minus, what's the derivative of a 42x squared? 84 with an x, very good. What's the derivative of 270x? 270, and the derivative of -10 is 0, so we don't need to worry about it. Okay, so since we have a polynomial, and a polynomial is a continuous graph, or a continuous function, and it's differentiable, we're going to set this derivative now, y'all, equal to 0. So we're going to set the polynomial equal to 0, or set our derivative equal to 0, and we're going to solve for x. So the first thing, y'all, since we're trying to solve this equation here, we can probably factor out a 6. Okay. So if I factor out a 6, that's going to leave me with an x squared. I don't know. I'm going to take my calculator so I can figure out what's 84 divided by 6. 14, and then 45 right here. Thank you, John. Okay. Now, the next step, y'all, we're going to do some factoring. So remember, the number in front of my x squared is a 1. So 1 times 45 is 45. Does anybody know any two numbers that multiply? Oops, I forgot an x right here. Anybody know two numbers that multiply to 45 but add up to a -14? 5 and 9, both of them negative, right? Because they multiply to a positive 45, they add up to a 14. Okay, so look, we're going to go like this. 6, x minus 5, x minus 9 equals 0. Okay? Y'all, the next step, we're just solving this equation. So we're going to set each part equal to 0. X minus 5 is 0. x minus 9 equals 0. So does everybody agree we're going to end up with x is equal to 5? Okay, so good question. Think about this. Look what it's saying. Everybody agree that the operation here is multiplication? Okay, so if we're multiplying a series of numbers together, y'all, and it's equal to 0, then one of those numbers is going to have to be 0. But the only parts that could be 0 would be those. You know why? Because that's always going to be 6. So I can basically disregard it. I'm only looking at the parts that have the variable components, right? If I multiply 3 numbers together and I get 0, I know that one of those numbers is 0. But you know what? I also know that one of those numbers is 6. And 6 isn't 0, so I'm not going to worry about that. I'm just going to figure out the value to make this. Huh? Yeah. Uh, probably more like element algebra. We do it in college algebra as well. So look, we came up with 2 critical values. Look at the direction. It says the smaller one is and the bigger one is. What's the smaller one? What's the bigger one? There we go. We found our 2 critical values. It's asking me what are the smaller and the bigger ones. We found it. Okay. All right. So let me keep scrolling here a little bit. Okay, now we have something about local absolute extrema. Okay, so it says, let f be a continuous function over a closed bounded interval. The absolute maximum of f over that interval and the absolute minimum of f over that interval must occur either at the end point of the interval or the critical point. Okay, so this part here is really, really important. You know, I want to explain something again. I'm going to draw a rough picture here. So here's my x-axis, here's my y-axis. Okay. And here's my A, and here's my B, and I'm going to draw a function. Okay, my function is going to do something like this, and it'll stop right there. Okay, and actually, I'm going to fix this a little bit. Yeah, that's good. Okay, so what I'm trying to point out here, y'all, is that we're talking about absolute maximum and absolute minimum. Okay, just the way the graph is drawn. So this is my point f of A, and this is my point f of B. Which one is lower? F of A, right? Okay, so what we're saying is the absolute minimum over that interval is right there. Where is the absolute maximum? The absolute maximum would be right about here, right? Okay, the tangent of that line, y'all, the slope of the tangent line would be 0, right? So what the theorem is basically telling me is that my absolute maximums and absolute minimums, they're either going to occur at the end point or they're going to occur whenever we have critical values. Okay? So let's take a look here. So this is how we're going to do the problem. So it says consider a continuous function f defined over the closed interval from A to B. Step number 1 says we're going to evaluate f at those endpoints A and B. Okay? And then part 2 says we're going to find all critical values of the function that lie over that interval, and we're going to evaluate it at those critical points, and then we're going to compare values. Okay, so let's go through steps. Let's go through the problem. Let's see if we can figure this out. It says consider the function f of x equals 3 minus 3x squared, and we're looking at the closed interval from -5 to 1. Okay, step number 1 says we need to evaluate it at the endpoint. So y'all, we need to find f of -5, and we need to find f of 1. Okay, so f of -5 is 3 minus 3 times a -5 being squared. Okay. So f of -5, this would be 3 minus 3 times, everybody agree -5 squared is 25? And so 3 minus 75, is that not a -72? Okay. We also need to do this, y'all, at f of 1. And are you all coming up with 0? Okay. evaluated the function at the endpoint. Okay, step number 2 says we got to find the critical points of f. The way we find the critical points of f is we need to find f prime of x. Okay, so we're going to take the derivative of this function. Question, what's the derivative of 3? 0. What's the derivative of a negative 3x squared? Negative 6x. So f prime of x is just a negative 6x. Now what we're going to do is we're going to set the derivative equal to 0. Okay? So we set the derivative equal to 0, and we solve for x, and we're coming up with x equals 0. This here, y'all, is my critical value. Okay? Just like we evaluated the function at the endpoint, we also need to evaluate it at those critical values. As long as those critical values fall within my endpoint. And 0 is a number between -5 and 1, isn't it? Okay, so now we got to find f of 0. Remember what we're going to do, y'all? We're just going to come back to my original function. Everywhere we have an x, we're going to put a 0. So f of 0 is equal to 3. Okay? Okay, now that we've done that, we're going to come back to our problem. Look what it says. The absolute maximum value is. We're going to do a stare and compare, y'all. We're going to look at this number, and this number. Which is the highest of those three? 3. We got 3 when we plug in x was equal to what number? 0. Okay? The absolute minimum. What was the lowest of those 3 values? -72. And that occurred when we plugged in x was equal to what? There you go. This right here, y'all, is the essence of 4.3. Let me ask you a question. Before I go on, is it making sense so far? But remember, we plugged it in, right? So remember what we did? We plugged in the 2 endpoints, right? And then once we find the derivative and we set it equal to 0, whatever we get for x, that's my critical value. So I have to evaluate the function at that value. Jennifer, as long as that value falls within those numbers. So I'm going to make this up. Suppose the value of x you would have come up with would have been 7. I wouldn't do it because I have to be between the 2 numbers, negative and 0. At 0. Yeah. It's going to be the derivative at 0. And so we evaluate at the endpoint, and we evaluate it at the critical values, as long as the critical values, John, fall within the endpoint. Does that make sense? Well, it's not that it would, if the critical value what we would have come up with would have been outside the interval, we just wouldn't evaluate it at, because we're trying to find what is the absolute highest and lowest point in that interval from -5 to 1, and it's either going to be at the endpoint or it's going to be at those critical values. Does that make sense? Good, good. Okay, look, y'all. Same type of problem here. We're going to do the same thing that we did before. So the absolute maximum of f and the absolute minimum. Okay, so remember, step number 1, y'all, we're going to find the function evaluated at the endpoint. So I'm first going to find f of 0. Okay, so look, I'm going to do it like this, you guys, because I'm going to evaluate this function at least a few values. This would be my recommendation. If I'm sitting where you're sitting, I would go to my graphing calculator and I would go to y equals. Okay, and if you have anything there, clear it out. And then what I would do, I'm going to type in the function that we have. So 6x squared, x squared, minus 6x, and then plus 11, right? Okay, and then hit enter. All right, then go ahead and quit this, and then go to the bars button, and go to y bars. So over here, just move the little arrow to the right, and then we're going to go to number 1, which is function. So we're going to evaluate, and I'm doing function 1, so I'm going to go ahead and hit 1, and I'm going to evaluate this we said at 0, right? So when I evaluate at 0, the answer is 11. So f of 0 is 11. And then we're going to do this again, but now we're going to evaluate it at what? At 10, right? So again, look, y'all, I'm just going to go to var. I'm going to do my little right arrow here. I'm going to hit number 1 because I'm at function. I'm doing my first y1, right? And we're going to evaluate this at 10. And at 10, 551. Isn't it a super nice feature? It just tells me, you know, you don't have it on the, you gotta have it on the player.
I actually do the equipment that is slower than using mathematics.
Okay.
To make a table and then insert the endpoint at the table.
Okay, so let's take a look here, y'all. Okay, once we've done that, remember, we got to find the derivative. So look, I'm going to take the first derivative of my function. So the derivative of 6x squared, everyone agrees at 12x? And the derivative of a negative 6x is a minus 6? Okay, and we're going to set that now equal to 0. So we're going to go 12x minus 6 equals 0. And we're going to solve for x. So when I move that 6 over, it becomes positive. Divide everything by 12. And we're coming up with what? X is a half. Remember, y'all, this here is my critical value, right? Okay, so we have one last thing that we need to do, y'all. We need to find f of 1/2, right? So again, look, I'm going to come back to my calculator. I'm going to go to vars. I'm going to go to the y bars. I'm going to go to number 1 function. I'm going to hit number 1 again, and we're evaluating this at 1/2. So I'm going to go 1/2. You can put 0.5. You're going to get the same thing, and 9.5. Okay, so now that we have that, the absolute maximum of f of x on the given interval, look what it says, is at x equals. Okay, what was the biggest value that we came up with? 551, but it happens when x was what number? At 10, right? So right here, y'all, I'm going to put 10. And the absolute minimum was 9.5, and that happens when x was what? 1/2? What do you think? Is that making sense? Well, isn't 1/2 between my numbers 0 and 10? Yeah, so guys, remember, your critical value, you are getting evaluated as long as the critical value falls within that closed interval. You're looking at the 9.5? Yeah, but remember, the interval that I'm looking at is this one here, right? Yeah. Okay. So look, same thing here. Same type of process, though. It says find the maximum and the minimum values of the function g of theta equals 4 theta minus 5 sine theta over the interval from 0 to pi. Okay, so just like we did before, y'all, I'm going to write out my first step. I'm going to find g of 0, and we're going to find g of pi. Okay, so I'm going to come back to my graphing calculator. Okay, first thing I'm going to do, y'all, since my interval is from 0 to pi, I want to make sure, and I'm talking about trig functions here, I want to make sure that we're in radians. Okay, so let me just make sure I'm in radians. I'm going to go to mode. Yeah, we're in radians. Okay, so let's get out of there. Okay, so now let me go to y equals. Guys, if you want to get rid of the function you have there, just hit the clear button. It goes away. Okay. You can go to y2 and just type in a new function if you want to, but I just cleared it out. So I'm going to go 4x minus 5 sine x. Okay, there's my function. And I'm going to enter that in. Okay, so let me quit it now. And I'm going to go to vars. I'm going to go to y bars. I'm going to go to my function. We're doing a y1. And we're evaluating this at, I want to say we did this at 0. So parentheses 0, and I'm coming up with 0. Okay. And then we're going to do the same thing that we did right now, and we're going to evaluate it at pi. And I'm coming up with a 12.5664. And this is approximately, okay. All right. So for my next step, y'all, we need to find g prime of 0. Okay. So let's see. What's the derivative of 4 theta? 4, right? Because it's the number, and so again, think about it as like 4x of b4, right? Minus 5. What's the derivative of a sine theta? Anybody remember? What's the derivative of sine? Cosine theta, right? Yeah. And now we're going to take this part here equal to 0, right? Because we take the derivative and then we set it equal to 0. So we're going to go 4 minus 5 cosine theta is equal to 0. Okay. And so let's see. For the next step, you guys, we're going to go ahead and solve. So this is going to be a minus 5 cosine theta equals a negative 4. And we're going to divide everything by negative 5. So I end up with a cosine theta equals 4/5. Does anybody remember how do I find the value of theta if I know the cosine of theta is 4/5? How do we find the value of the angle? Does anybody remember that? John, do you remember that from last semester? Okay. Okay, so very good. So guys, Jennifer's question is it on the sheet? Okay, so we could go to the sheet, right? Let me come back over here. Oh man, where am I? Here we go. Okay, so we could go to the sheet, right? And we could pull it up and we could say, look, we're looking for cosine. But do you see a 4/5 here anywhere? No, right? Okay. But that's an excellent point, Jennifer. That would be my first approach to see if it's there. Y'all, when it is not there, what we say is we say, look, the way we find theta is we're going to take the inverse cosine of 4/5. We're trying to figure out what was the angle, what angle did I have to use so that my value was 4/5. And so what we're going to do here, y'all, is this is going to be an approximation. That's why I'm kind of putting the little squiggly. Use my calculator. And I'm going to say, what is the cosine inverse of 4/5? Okay. And look at the value that I came up with. We came up with a 0.6435, right? Again, I'm going to 4 decimal places here, y'all. So 0.6435. Remember, this here is my critical value, right? That's my critical value. So question, before I go on, would you say that 0.6435, is that in the interval from 0 to pi? Well, let's think about it this way. When you were back like in 9th grade, 10th grade, what was the approximation that we used for pi? 3.14. So isn't 0.6435 between 0 and 3.14? So like, okay, yeah, we go. You see what I mean? So guys, if the answer we would have come up with, I'm just going to make this up, but if the answer we would have come up with, say, would have been a negative value, or we would have come up with like a 5 point something, then we'd say, hey, you know what? I'm not going to sweat it because it has to be in the bounds of that interval. So now, y'all, we're going to find this. Now we're going to find g of 0.6435. Okay. So I'll come back to my value, my function here, right? 3/5? Oh, no, but why 3/5? Oh, because no, but you just changed it to a sign. You said okay. Yeah. So look, I'm going to come back over here. I'm going to go to my y bars, go right there, function, number one, and I'm entering in 0.6435. And if you want to be even more, you can enter in exactly what we had here, cosine inverse of 4/5. Or guys, the other thing you could do, put a few more decimals. Right, you could do something like that if you wanted to. Hit enter, and look at the value we came up with, a negative point. If I'm rounding to 4 decimal places, everybody agree with a negative 0.426? What do you think? Right? Negative 0.4260, right? Okay, so here we go. And we got our 3 values, okay? Now, I want you to notice the directions, y'all. The directions say, what is the minimum value? So now I'm actually looking at the values that we came up with. What was the lowest value we got? The negative 0.4260, right? What was the biggest value we got? There you go. And those would be the 2 values that we use. So what do you think? Is 4.3 working so far? Steve, we're doing okay? Yeah. It's pretty easy, right? It's pretty straightforward. Yeah. That was another reason I wanted to do this one today, y'all. It's right before spring break. I didn't want to throw anything. You know what I mean? I want you guys to be able to enjoy your spring break. And if I was sitting where you're sitting, I might, you know what? Look, 4.3 is pretty easy. If I don't want to sweat it, maybe I'll knock it out this afternoon or tomorrow or something. So just, or maybe I'll say, hey, I'll wait. I'd probably knock it out just because it is pretty straightforward, and I don't want to have to worry about anything over spring break. You know what I mean? But yeah, that was kind of my reasoning behind some of this stuff. Okay, so let me keep moving over here, and let's take a look. It says find the relative maximum and minimum of y equals x to the third minus 75x plus 13. Okay, so yes, if we're looking for relative maximums and minimums, guys, notice they did not give me an interval here, but we're still going to find the derivatives, okay? So look what it says. Step number 1 says find y prime. Okay, we can find y prime. 3x squared minus what, 75? That's it. So right here, y'all, I'm just going to write in 3x squared minus 75. Okay, now to find my critical values, remember, to find my critical values, I'm going to take the derivative here, and I'm going to set it equal to 0. Okay. So, y'all, one of the things I think, when we're doing the calculus part is just to make sure that our algebra is solid, okay? So I'm going to kind of do some of the algebra here so that, again, you have practice with this and you kind of, make sure that those skills are nice and honed. Remember, I'm going to first factor out a 3, and I'm left with an x squared minus 25 equals 0. And then there is the difference of squares formula. The difference of squares formula, again, maybe you remember this, maybe you don't, but in case you don't, I'm going to show you right now. When this piece is a perfect square, and this piece is a perfect square, and there is a minus in the middle, that's why it's called the difference of squares. It has to be a minus, okay? If it's a plus, it's not going to work. Then what we say here is, we say, okay, look, what do I need to square to get x squared? Oh, x and x. What do I need to square to get 25? 5 and 5. One of them is negative, one of them is positive. Okay, that formula always works. Okay, and I'll even write it down here for y'all so you can see it. But it's this formula right here. A squared minus b squared is a minus b and a plus. Okay. All right. Remember what we're going to do. We're going to set each of these parts equal to 0. So when I set the first part equal to 0, everybody agree we're going to get an x equals 5. And when we set this one equal to 0, y'all agree we're going to get an x equals negative 5? Okay, so remember, we're looking for the relative maximums and the relative minimums. So the way we're going to do this, y'all, once we found our two critical values, we're going to find, well, they're calling it y, so I'll use y notation, but we're going to find y of -5, and we're going to find y of +5, okay? And we're going to take a look at those two values. So again, one more time, y'all, I'm going to come back to my calculator, okay? I'm going to turn it on. There we go. I'm going to go to my y equals, hey, I don't need that first function anymore, so I'm going to go ahead and clear it. And I'm going to enter in the new one that I got. We have x to the third minus 75 with an x and a plus 13. Okay. Enter that in. Okay. So let me quit that. Let me go to my bars. Let me go to my y bars function. We're doing the first one. We're evaluating this one at -5 and then at +5. So look, at -5, y'all, I'm coming up with a 263. Okay. 263 at a -5. Okay. And then let me evaluate it at +5. So bars, function, the first one. Now at a +5, I'm coming up with a -237. Okay. So now that we've done that part, we're going to go ahead and just enter our answers in. So the maximum is at 263, and the minimum is at a -266. 260, oh, 237, sorry. I'm sorry, Jennifer, say that again? So yeah, once we found our critical values, we came up with 5 and -5. So we came back to the original function, and everywhere we had an x, we plugged in a -5, and we plugged in a +5. So at -5, we came up with 263. That was our maximum, right? And because this is negative, that's going to be my minimum, right? And you know why we didn't evaluate it at any endpoints? Because they never gave us an interval to begin with, right? They didn't give me that interval. So when it says find the relative maximums and minimums, we still do the derivative. We still set them equal to 0, and we still evaluate the function at those points, and then we just say, okay, which was the highest and which was the lowest, right? You came up with something different? Okay, you know what? Maybe I entered in my function wrong. Let me see. Let me double check. Y x to the third minus 75x plus 13. Let's see. Okay, so let me see. That looks right. 13. Okay, so then let me come back here. Let me quit this. So y bars. Are we good, Steve? -5. Still coming up with 263. You know what? Let me do it by hand just to make sure that we're good. So it's possible I made a mistake, but let me see. So y equals x to the third minus 75x plus 13. Okay, so if I go -5, -5 to the third minus 75 times -5 plus 13. So that's a -125. -75 times another -5, so 75 times 5, 375 plus 13. So I have a -125 plus 375 plus 13. Yeah, I'm still getting 263. Okay, yeah. Yeah, good point. Okay, so good point. Yeah, we got to plug it into the original function, right? So we use the derivative to find those x values, and then we take those x values out and we plug it back into the original function. Good point. Good, good, good. But I'm glad you asked me anyway, because this is just making sure that we were doing it the right way. Okay, we just kind of did it by hand here. Excellent point. All right, y'all. So let me keep scrolling here. Let's see if we got another one here. Okay. So um, same kind of thing here, y'all. The same sort of problem because the function f of x equals 2x squared plus 12x plus 50 has, and you're going to click on this thing right here, y'all, when you do this, and it's going to say either maximum or minimum, right? You're going to do that kind of thing. Okay, so look, let's take a look. First thing I'm going to do, I'm going to find my y prime, or f prime of x, because they're using f notation. So let's take the derivative. What's the derivative of 2x squared? 4x. Very good. What's the derivative of 12x? Plus 12, and the derivative of 50 is 0. Okay, so we're going to take this piece right here, y'all, and we're going to set it equal to 0. We're going to find our critical value. So 4x plus 12 equals 0. 4x equals a negative 12. Everyone agree x is a negative 3? Can we divide both sides by 4? Okay, so now what we want to find, y'all, is we want to find f of negative 3. Okay, and I'm probably getting a little spoiled here because I'm going to come back and I'm going to enter this in this way, but hey, that's what I like being spoiled a little bit. So 2x squared plus 12x plus 50. And enter that in. Okay, let me split this. Let's go to bars. Let's go to our y bars, do our functions, and let's evaluate this at, we said, negative 3. And let's see, 32, right? Okay, so we're coming up with 32. 32 at x was equal to what value? Okay, now this is the question, y'all. Is it a maximum or is it a minimum? Okay, that part we don't know yet. Okay, we don't know that part yet. But let me ask you a question. Does anybody know, or does anybody remember, what was the graph of 2x squared plus 12x plus 50 look like? What is the basic shape of an x squared graph? Anybody remember? Do y'all remember the basic shape of an x squared graph? It's a parabola, right? So guys, parabolas either do one of two things. They either open upward or they open downward. Okay, so I want to point something out. What we found, y'all, was we found that point. That's the vertex, okay? So parabolas, y'all, look kind of like a bowl, and it either opens up or it opens down. And what we found, every time we do the derivative of a parabola, y'all, in essence, what we are finding is we are finding the vertex, which is either going to be the highest point or the lowest point. Now, the way you know on whether or not my graph will open up or down is we look at this guy right here. Not even or odd, if it's positive or negative. If the number is positive, then the graph is going to open upward. And if the graph of the number is negative, then the graph is going to open downward. Okay? So in this case, because this number here is a positive number, and guys, it doesn't have to be 2, it could be 0.2. As long as it's positive, the graph's going to open up. If that number would have been negative, then the graph is going to open down. So since the graph opened up, would we say this is a high point or a low point? Low point. So we're going to call that a minimum. Okay, it's going to be a minimum. All right, and again, because it's a parabola, y'all, parabolas either open upward or they open down. Okay, and the way you know is if the number a is positive. If the number a is positive, hey, the graph opens up. And if the number a is negative, the graph opens down. Again, y'all, that's something that we do in college algebra. But again, I know it's probably been some time. Some of you may have had college algebra. Some of you maybe did like a dual enrollment in high school, or some of y'all just maybe placed in here. So it's something that we need to know, but it's okay if you didn't know it. the point is now we know. Okay, so if you didn't know, hey, don't sweat it. Now we're good. Okay, so now again, some of this y'all is kind of like review stuff in college algebra. Like I feel like if like I'm teaching college algebra right now, and I feel like if some of those kids were in this class right now, they would know the answers to these questions. But just because we did this like last week, you know what I mean? Not because like they didn't know it 2 weeks ago, but they know it because of last week. But it's okay. We're gonna figure this stuff out. So what we're talking about now is when the functions are increasing and decreasing. Okay, so I want to mention something here about this particular graph, y'all. Do you notice that we don't have absolute maximums or absolute minimums because again, the graph goes up forever and the graph goes down forever. But do you agree that we have local maximums and local minimums, right? So would you agree with me that this is a minimum value? And would you agree with me that that's a maximum value? Okay, this is what I'm going to do, y'all. I'm going to draw like a vertical line right here, and I'm going to draw another vertical line right here, okay? Now, we're going to think about where the function is either increasing or decreasing. Increasing, y'all, means the function is going up. Decreasing, function is going down. Okay. The reason why I drew those two vertical lines is those vertical lines, y'all, are going to kind of be like the boundaries for where the function is going up and the function is coming down. Okay. So what I want to ask you guys is, if I were to start, let me go over here. If I were to start from the left and I'm coming in this way, look at my y value. Is my function going up or going down? Okay, so from negative infinity up until we get to this value right here, the function is decreasing. So we're going from negative infinity to this value here was a -1. The graph was going down over there. Okay. Now I want to point something out again. I'm going to draw my vertical line again. Okay. Then we're still moving between these two values here, between the two green vertical lines. Look at the function. As I'm going from the left to the right, is my function going up or down? It's going up. So it's increasing. It's increasing over the intervals from, everybody agree that's -1 to 2? Okay. And then y'all, we keep moving to the right of 2. So as I move to the right of 2, the function is going up or down? Going down. So because it's still going down, we're going to put a union because it's going down between 2 and infinity. The union just means that it was going down over two parts. It was going down from negative infinity to -1, and then it started to go down again when we were going to the right of 2. The union just means that there's two separate times when the function will decrease. So we got to connect those two parts. The union connects them. Okay. What I, the part that I kind of, that we kind of, where we kind of thought about the calculus portion of it, y'all, was just in finding those critical values, because the function is going to be increasing and or decreasing around where those critical values occur. Okay. The other thing I wanted to emphasize, y'all, my intervals are going to be open intervals. So they're not going to use brackets, they're going to use parentheses at these things here. All right. So we got a few more problems to do here, y'all, in 4.3. And these problems, again, are dealing with costs and profits and revenues and all that kind of good stuff, okay? So remember, there was one day in class that we talked about that little taco truck, right? Pepe Le Pew's taco truck and stuff. And I said, okay, look, there's a cost function there's a revenue function, and then we find the profit. Okay, so the nice thing about this problem, y'all, they already gave us the cost function. Okay, so let me clean that up a little bit. They already gave us the cost function here. They gave us what they call the demand function. The demand function, y'all, is just the price. Okay, so what are we selling? I don't know, but every one of those things is going to go for $1,110. Okay, so the first thing we're going to do, step number one, we're going to find what we call the revenue. Okay, remember, the revenue is how much money we bring in. Okay, so the way we find the revenue function R of X, we're going to take the price, P of X, and we're going to multiply it by X. We're going to multiply by however many items we sell. So we know that our P of X was 1,110. We're going to multiply that by X. That is our revenue function. Okay, so we found our revenue. Okay, we're looking to maximize what we call the profit. Okay, so step number two, we're going to find P of X, which is our profit function. Okay, the way we find the profit function, you guys, the profit function is always going to be the revenue function minus the cost function. The revenue is how much money we brought in. The cost is how much money we spent. So if I take all the money that I bring in and I subtract all the money that I spent, whatever I'm left with is my profit. If you've ever heard the term, oh, we're in the red, what does that mean? That I spent more money than I brought in, right? That's what we say we're in the red or we're in the negative, right? We want to be not in the red, right? We want to bring in more money than we're spending. Okay, so now we're going to go ahead and write this out. P of X is equal to the revenue function, which we were saying was 1,110x minus the cost. Now, guys, I'm going to write this in parentheses because I am subtracting the entire thing here. So 1750 plus 370x plus 1.1x squared. Okay. And we're going to worry about combining like terms here. Okay. So look, I bet you we can combine those x's together. So 1,110 minus 370, 740, thank you so much. 740 with an x minus a 1750 minus a 1.1 x squared. Okay, excuse me. This is the function that we are looking to maximize, okay? So take a look, you guys. I'm going to find my critical values now. So that's going to be my step number 3. Let's find our critical values. Remember, the way we find the critical values is we're going to take the derivative of our profit function and set it equal to 0, right? So the derivative of 740x would just be 740. The derivative of 1750 is 0, so I'm not going to worry about it. Anybody know what is the derivative of a minus 1.1x squared? What am I supposed to do with the 2? Negative 2.2x, right? We got to take the 2, we got to multiply it by the number in front of my x, and then subtract 1 over. That's right. So guys, John says, now we're going to take this equation, we're going to set it equal to 0. So 740 minus 2.2. And I'm coming up with like 336.36363636. Okay. So x is equal to 336.36 36, 36, 36. So on and so forth, right? Okay. Finally, step number 4. Let's find P of 336.36.36.36.36. Yeah, you can put the line above the 36. That'll work too. Okay, so look, y'all, I'm going to come back to my calculator, right? I'm going to go ahead and go to my y equals. I'm going to clear that first function that we had, and I'm going to write in my profit function. So remember, my profit function is the one that we have right here, the 740x. So we're going to go 740x minus 1750 minus 1.1 x squared. I hit x squared. There we go. Enter that in. Okay, so now I'm going to quit this. I'm going to go to my bars. I'm going to go to my y bars function number 1, and we are entering 336.3636363636. Okay, there we go. All right, I just threw a few of them in there. All right, and now we're going to hit enter, and here's my answer. Okay, guys, remember what we're finding? We're finding the maximum profit. So we're talking about cash money, aren't we? So I'm talking about cash money. How many decimal places do you think we're going to go to? 2, right? So everybody agree $122,704.55? Okay. 122,704.55. 122,704.55. And that right there, y'all, is going to be, oh, okay. Well, we did a little bit extra. I didn't do a good job of reading the directions. It just says find the production level that will maximize the profit. That would have been the 336.36 with a little line, right? Because it was asking me how many do we have to make. Okay. Yeah, because of look at the directions. See how the directions say find the production level that will maximize the profit? So it'd be 336.36, right? We found what the profit was. The maximum profit was that value, but that was being plugged into 336.36. Right? Good deal. Yeah, let's take a look at the next one, y'all. Okay, so I think we got 2 more after this. Yeah, there's 2 more. Okay, so let's take a look here. It says the function f of x equals 2x to the third minus 24x squared plus 72x plus 1 has a derivative. They took the derivative for us. How nice. Okay, it has one local minimum and one local maximum. Okay, let's figure out when these things are going to occur. So remember, y'all, they already took the derivative, so we don't have to do that. We're going to find our critical values by taking the derivative and setting it equal to what value? Very good. Okay, everybody agree we can probably factor a 6 out of everything? So 6 out of x, 6x squared is x squared. 6 goes into 48 8 times. 6 goes into 72 12 times. Okay. So y'all, again, we should be able to factor this one here, easy breezy, cover girl. So look, I multiply 1 times 12. That leaves me with the 12. Anybody know 2 numbers that multiply to 12, but when you add them together, would give you a negative 8? 6 and 2, both negative, right? Because if we multiply a negative 6 times a negative 2, there's our positive 12. If we add them together, there's our negative 8. We're going to set each of them equal to 0. So look, y'all, when we set each part equal to 0, everybody agrees we're going to get an x equals 6 and an x equals 2. Okay, we're looking for the maximums and the minimums of the function f. Where do I need to plug those numbers into? The derivative or the original one? The original function. Very good. So look, y'all, we're going to find f of 2, and we're going to find f of 6. Okay, so again, I'm going to come back to my calculator, right? I'm going to clear this out, and I'm going to enter in 2x to the third minus 24x squared plus 72 with an x, and then plus 1 finally. Guys, I want to say that when you're doing this here, this is probably where, if I'm going to make a mistake, it's probably going to be where I'm entering in, right? So if I just hit the wrong button, or I thought I hit the squared and I didn't, something like that. This is probably where I would make a mistake. Okay, so enter, and then quit it, go to vars, come to number 1, and again, we're evaluating this at 2, and at 2, we're coming up with 65, and we're going to do this again, but now I'm going to evaluate it at 6, and I'm coming up with 1. Okay, and so again, let's go ahead and answer the question. So it says f of x has one local minimum and one local maximum. The local minimum occurs when x is equal to. So again, y'all look, I'm going to look at my two answers that we came up with. Which is the minimum? What's the lower value? Yeah. So the lower, this is my min, and that's my max, right? So look what it says. It has a local minimum when x is equal to, when x is equal to 6, the value was 1, right? And the maximum occurs when x is equal to 2 with a value of 65. So again, I just want y'all, like the reason why, you can see like the problems we've been doing are very repetitive, right? We're doing the same thing over and over. I just want y'all to be aware of the way the problems are worded, right? Sometimes they're worded one way, sometimes they're worded another. We just have to pay a little close attention to that. But the ideas are still very much the same. Okay? Huh? Finding maximums and minimums. Yeah. So look, let's take a look at the last one here. The total revenue in dollars of micro drones. Okay, so look, y'all, first thing I'm going to do, they're telling me the revenue. So that's my function R of X. So I'm going to just write that out real quick. R of X is a 39X minus a 0.3, or 0.03, I should say. 0.03x squared. Where X stands for the number of drones. How many drones must be sold to maximize the revenue, and then find the maximized. Okay, so we're looking to find the maximum. So we're going to find R prime of X. The derivative of 39x, everyone agree, is just 39? What is the derivative of a negative 0.03x squared? I'll give you a hint, it's going to be negative. Very good. What an X, right? Perfect. You guys are doing great. Okay, now we're going to find our critical values. So we're going to set this thing equal to 0. Okay. So I'll actually move that the other way. And so now we're going to divide 39 divided by 0.06. And I'm coming up with 650. Okay. Okay, so we came up with our value of X. We came up with X 650. Look at the question. It says, how many drones must be sold to maximize revenue? Guys, I want you to look at my revenue function. Isn't this a parabola because it's an X squared? Right? So again, think about it. It's a parabola. It has an X squared. It doesn't matter that the X squared comes later in the equation, but that's the highest power of the X. Look at the sign of the number in front of the X squared. It's negative. What does that tell me? That my parabola opens down, so that is going to be my maximum, right? So look, the total number of drones to maximize revenue, we came up with 650. So we're going to put a 650 right here. part B says, can we find R of 650? Of course we can. We'll come back over here. We'll go y equals, clear that one that we have there, and I'm going to enter in a 39x minus a 0.03 x being squared. Enter that guy in. Okay, so let's quit it. Go to bars, go there, go to number 1. Let's evaluate this at 650. And I'm coming up with a 12,675. And there's our guy. And that looks like I put a point there, and there's no point. 675? Yeah, there it is right there. 12,675. And we found our maximum revenue. What do you think? 4.3, did it work? Still okay about it? Not too bad, right? Okay, so guys, again, because today's the day before spring break, do we have time to do football training? We probably do. I don't want to do that before spring break, right? I want y'all to be able to enjoy your spring break. So again, let me do something real quick, you guys. Let me get out of here. Yes, we're recording. All right, wait, we got some folks here. So Angela, Julio, Matias, Noel. Guys, those who are at home, did this make sense, what we did today for 4.3? Do you guys feel okay with any of these problems that we did?
Mine was kind of cutting off, sir.
Let me raise it up a little bit. Okay, I'm sorry, go ahead.
Mine was cutting off, kind of like the video feed was cutting off on my end. I had to reload the
Anybody
session.
else?
On mine it was fine, sir.
Okay. Okay, so Matias, it might have just been your internet because Julio says he was good. Julio, did we do okay with these problems?
Yes, sir. Everything fine.
Okay. Okay, good, good. So guys, it is recording. Let me go ahead and stop recording now.